Okay, let's do just a couple more examples with the geometric before we move on to the next one. Suppose it's your job to blow up the Death Star, and you've been informed that the target you need to hit is approximately the same size as a womp rat, and you are used to bullseyeing womp rats about 6 out of 10 times back home. How many shots is it likely to take you in order to hit this target? Right? You only need to hit it once. Repeated trials until you get a success, then you stop. That's the definition of a geometric distribution. And since we're asking how many shots it's likely to take, this is a range of likely outcomes as opposed to finding a specific probability. So for the range of likely outcomes, we need two things. We need mu, which is the mean, which is 1 over the probability. If the probability is 0.6, 1 divided by 0.6 is going to be about 1.67. And our standard deviation, our sigma, is the square root of 1.67 times 0.67. Right? Just the square root of this times 1 minus that. And that comes out to be about 1.06. Okay, if we double this, we'll get 2.12, and subtract it from that, we get a negative number, which means the low end of our range is 0. Always the case with a geometric distribution. And if we double that, well, we already doubled it. We got 2.12. Add that here, we're going to get 3 point something, not quite 4. So 0 to 3 is our range of likely outcomes. So it's not likely to take us more than 3 shots. And this is important information because we know how many people we have to put in the red squadron to be demolished before the job is done to make the movie as exciting as we possibly can. Now, let's check if this works out with our cumulative distribution function, because remember, the range of likely outcomes should give us 95% probability. So if we go to second, distributions, geometric CDF, 6 out of 10 is 0.6, and we want to know the probability that would be from 0 up to and including 3, we get 93.6%. So yes, that is our likely range. It's almost never going to be exactly 95, but if we went any higher than that, just to illustrate, if we were to do exactly the same thing again, but go to 4, then it's going to be more than 95. So 3 is the highest one that will give us less than 95% probability there. Okay, let's go from outer space, or a galaxy far, far away, I guess. You've got to a cowboy movie. You've probably all seen when you've got the good guy trying to shoot the little lever that will switch the train track over and prevent the train from going off the cliff into the canyon. Well, suppose that's you. You've got 5 shots in your rifle, and you need to flip the switch to save the train. Your average at that distance is about 0.45, which oddly enough is the same as the caliber of the rifle you're shooting. What's the probability you are going to get that target within the first 5 shots? And again, this is a cumulative distribution. We've got a probability, our P, of 0.45, and we want to know what the likelihood that we have a success within the first 5 shots is going to be. So almost the same as what we just did. Go to distribution, go to CDF, 0.45. What's the likelihood you're going to get it within 5 shots? Now, don't turn your brain off just because you're letting the calculator do your work for you. You should also think that this is about half. This is almost half of the time you hit your target. So how likely is it that you're actually going to miss the first 5 times? That's not very likely at all. So the likelihood that you're going to get this within the first 5 shots should be really high. And it ends up being 95%. I apologize, I didn't check the numbers. I would have changed it if I realized it was going to be almost the same as our previous question. But we've got a 95% chance here of saving the train, which, again, if you pay attention to the context of the question, is sensible for our answer. Next time, we're going to move on to the binomial distribution.